this quantum Fourier transform. So what's the easiest definition, or the simplest definition for this is QFT is effectively is a change of basis from in this particular quantum computing context stage. Basically, it's a change of basis from computational basis. Although you can use it for changing from one basis to another basis, but here it is the way we'll be learning it today. It's basically it's a change of basis from computational basis to the Fourier basis. So this basis is important. Okay, how you basically represent your information. So for example, if it is a 1 qubit case, 1 qubit, so the computational basis basis states, I can say, they are, or the vectors, basis states vectors are K0 and K1, right? And Fourier, for 1 qubit case, the Fourier basis for 1 qubit, or the basis states are plus gate and minus gate. Okay, so let us try to understand this visually. Is suppose this is the blosphere. So this is a very bad drawing, and so this is the zero vector, right? So that is gate zero state, and this is the one vector, okay, gate one state, pointing to the south pole, and this is to the north pole, right? And this is basically a representation of the, say, original basis gate x. Okay, gate x is sometimes gate 0 and sometimes gate 1, right? And if you represent this to x tilde, like this is the quantum Fourier transform, or the QFT transform of this basis states, and the representation looks like this. So suppose this becomes in the equator plane here, and this is here. Okay, so now I suppose write this 0 as 0 tilde here, and 1 as 1 tilde here. Okay, as the Fourier basis, say 0 tilde and 1 tilde as the Fourier basis, and Ket 0 and Ket 1 are the computational basis, right? So now can someone answer that what I should apply to this state so that I get this state? Can anyone point? Can anyone guess? You already know this, know the answer. Can anyone just write the answer here? Exactly. So you just need to do Hadamard. Correct. So Hadamard gate. So what is Hadamard gate? Hadamard gate is h equals to 1 upon square root 2, 1, 1, 1, and minus 1, right? So basically, if you apply the 0 state, that is 0 state Hadamard on the 0 state, you get the plus state. And if you apply Hadamard on the 1 state, if you apply Hadamard here, you'll be getting minus state, right? So Hadamard gate is the quantum Fourier transform for single qubit. So Hadamard gate itself performs the quantum Fourier transform for single qubit. Okay. So now let's build more number of qubits. Building quantum circuit Mathematically, they are same. Implementation is very different. Building mathematically, this quantum Fourier transform and the classical Fourier transform, they are same, but the implementation is very different. So now let us try to understand how this circuit is implemented and what is the mathematics for that. So building quantum circuits for this that applies QFT. Okay. So if it is a 1 qubit, we just we have seen that the computational basis states are Ket0 and Ket1. If it is 2 qubits, the computational basis states are 0, 0, sorry, 0, 0, 0, 1, 1, 0, 1, 1. These are the basis states for 2 qubits. And if it is n qubit, so you have 2 to the power n basis states, right? Basis states from all 0 to all 1, right? And let's define a capital N variable equals to 2 to the power n. Okay. So this is from the computational basis part. Okay. Now, if I apply the quantum Fourier transform, what will happen, right? So let us go back to the classical DSP definition, digital signal processing definition for this DFT matrix, right? So suppose my original basis is X, and if I apply the DFT matrix, suppose the DFT matrix is F, right? So then basically my transform vector is X tilde, say, right? X tilde is the Fourier basis. So classical signal processing theory, we have seen that normally people write in this way. So you have a vector X and you get some Y. Y is the frequency domain representation for the signal X. X vector, Y vector, and F is the DFT matrix, right? The same thing I have written. But what is then how this DFT matrix works? It basically 1 upon the square root n summation of y equals to say 0. This is a variable, simple dummy variable, y equals to 0 to n minus 1. This y and this y are not same. Okay, this is just a variable. So let's define this with another variable. Say this is some x tilde. Say okay. So so this is y equals to 0 to n minus 1 and e to the power 2 pi I x times y and get y by capital N. So this is a definition from definitions, right? So this is the representation of the how the DFT matrix originates, right? So this is the way of representing. So and times this times kx, right? So this is the DFT representation for this Fourier matrix, right? Now this is the Fourier basis and this is the computational basis. Computational basis, just we have seen like how the computational basis looks like, all 0 to all 1, right? Computational basis states. And this is Fourier basis state. Okay. Now, again, to implement the n qubit thing, let's again start with the single qubit case. Single qubit case first. So from the we'll follow this definition. Okay. So first is suppose n equals to 2 to the power 1 because it's a single qubit. So little n equals to 1. So capital N equals to 2. Right. So we defined a new variable capital N equals to 2 to the power n. So capital N typically coming from the classical picture and little n coming from the qubit, right? You take basically so what is the thumb rule here? So typically we normally choose number of qubit equals to the classical data length log ceiling function, floor function, okay? Or simply if you just remove the ceiling function. So for example, if you have classical say 10 data, right? So nearest is 3, nearest is 8. 8 means 3 qubit. So 2 to the power 3 qubit. But 10 for what? If you take the ceiling function of this, then it will become +1. So it will be 4 qubit. Hope it makes clear, right? If you have 15 classical data point, so floor function of log 15 will be around 4, right? So this is log 2 base. Okay. So basically, roughly, we normally take capital N equals to 2 to the power n, right? So classical number of data points or the Fourier basis points elements equals to 2 to the power little n. Little n is the number of qubit size. More precisely, it is basically ceiling function of the log capital N. This is more precise way of taking, and this is very vague way of taking. Okay. So now if you put capital N equals to 2 to the power little n equals to 1, that means a single qubit thing, right? Single qubit. Then capital N equals to 2 to the power 1, that is equals to 2. Then QFT of get x, okay, equals to 1 upon square root 2. Just let us try to write the definition. So what will happen? 1 upon square root 2, summation of y equals to 0 to 2 minus 1, right? And e to the power 2 pi I, in place of x is x and y we can, so 0 to 2 and x into y. Say, let's first write the equation, then we'll break it 2 and get y, right? If we write this way, then basically this becomes 1 upon square root 2 e to the power 2 pi I. If you break the summation term into two parts, like 0, 0 to it is 1, right? So let's take 0 and 1. Then 2 pi I x into 0, y equals to 0 by 2, get 0, plus e to the power 2 pi I x into 1 by 2, get 1, right? And more if you just this is x into 0, so e to the power 0, right? So what is remaining? So e to the power 0 is 1, so it will be 1 upon square root 2, get 0, plus e to the power I pi x, get 1. So I'll today I'll dive in a much deeper way so that you understand the circuit of the QFT easily. Okay. So it is not like you just simply give the equation and it will do the circuit design. There is more tricks in this. Okay. So what we get is QFT of x, right? So QFT of ktex, say QFT of ktex for single qubit is this one, right? Now, this is fine, but this is not Hadamard gate. It doesn't look like Hadamard gate, right? So let's prove like QFT of, suppose let's take our information as 0 itself, QFT on get state 0, right? So this is 1 upon a square root 2, 8, 0. And this x is now becoming 0, right? So it will be what? It will be get 1, right? So 1 upon a square root 2, 0 plus 1. So, and this is basically plus state. So this is like, this is the Hadamard gate implementation, right? Plus state. Similarly, QFT of kit 1 is basically 1 upon square root 2. The first is 0. And the second is e to the power I pi. And this one will be in place of x, it will be 1. So it is actually e to the power I pi, which is minus 1. Okay. So it will, this plus will become actually minus. Okay. So then this is minus. So this is minus kit, right? So we can easily verify that quantum Fourier transform of 0 is basically plus state and quantum Fourier transform of 1 is basically minus state from definition. This is proved from definition, right? Now we need to understand some notational thing. So when you basically read various textbooks, including Nelson Chuang and other textbooks, so you will be confused how the derivation is happened and why this kind of like various notations and all. So let me some point so to clarify this kind of doubts and all. So let's take a note on the notations. Suppose n equals to 3 qubit. Okay. So your x tilde, yes, that's what we just said. So if you apply Hadamard gate for 1 qubit, that is you are doing QFT for single qubit. from computational basis to the Fourier basis, right? So Ktex is basically if you have 3 qubits, by definition x tilde is 1 upon square root 8, and summation of y equals to 0 to 7, right? And e to the power 2 pi I x into y by 2 to the power 3 get y. Okay. And sometimes people, if you write in this way, and n equals to 3, so this get y will actually it will be get y will be basically, say it is you are computing for, say, ket 4, right? Y equals to 4, right? So then basically ket y equals to ket 4, right? So this can be the case, and sometimes there is a, like, you already have seen that computational bases are written in the binary format, but some books already written in 1, 2, 3, 4 formats and all. So basically, the way computer understand it is in the binary pattern. So it can be 0, 1, 0, or it can be, it's a 3 qubit thing. So it can be 0, 1, 1, etc. Right? In this form, actually, y should be represented. So if it is ket y equals to ket 4, then it means actually 1, 0, 0, right? So this is the binary number representation. Then what is the complications? So complication is how you represent this part. Okay. So for example, if it is summation of y equals to 0 to 7, y equals to 0 to 7, this part is there, like this particular form. Then it is equivalent to write as because y you can always represent as a series of bit string, right? Ket y, say for example, this is a vector, right? And this is like a you can write y1, y2, dot 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 yn, right? In this way, these are the bit string representation of the computation, like 0, 1, 0. So it instead of 0, 1, 0, you can write like coefficient y1, y2, y3, yn. So if there are 7 components, so y0 to y0 to y6, right? So here it is y0 to y7. So it is equivalent to write as y1 equals to 0 to 1 multiplied with summation y 2 equals to 0 to 1, y equals y3 equals to, for each bit string varying between 0 and 1, 0 and 1. So dot 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 up to summation of yn, if it is n, okay, yn equals to 0 to 1. So how you are representing your y notations? Okay, this is slightly tricky, but it will basically remove many confusion. So how I am using this information, I'll come. Why this is important? Okay, so okay, let's visualize how this thing's happening. This thing. So let me show you what Qiskit textbook material. So I hope you can see this browser. So this link, let me copy the link and share with this chat so that you can also open in your laptop. So if you see here, leave all this definition and all these things. So see, computational basis. So here is four qubits are shown. Let's say qubit 0, 1, 2, and 3. And the computational basis only changes between 0 and 1. See, 0, 1, 0, 1, 0, 1, and 0, 1, right? And once you apply the QFT, what is happening? See, so all this information that was basically polar shift between North Pole and South Pole, right? Swapping between the poles. Now they are on the equator, right? In the equator plane. And they are basically, the information that is changing here is basically the phase, right? So one important observation, if you see from right to left, how you represent your bit string. Suppose this entire information in the bit string is y0, y1, y2, and y3, or y1, y2, y3, y4. And here y1 tilde, y2 tilde, y3 tilde, and y4 tilde after Fourier transform, if you see. So the last bit string that is in the last qubit 3, is only changing 90 degrees, 180 degrees, if you see, right? If you see prior to that, after QFT, it is changing by 90 degrees. Prior to that is 45 degrees. Prior to that 22.5 degrees. So there is a phase relationship when we apply the QFT in the real scenario. how these things bases are rotated. So this animation will help you to understand how these things happening, and now I will tell you mathematically how it is happening. Okay, so there is a detailed tutorial, you may have a look, and implementation I'll show how it is done. Okay. Now now again let us write. So this part is bit tricky and mathematically bit intensive. Please bear with me. So x tilde is 1 upon square root n summation of y equals to 0 to n minus 1, suppose. Okay, classical points n minus 1, e to the power 2 pi I x times y by capital N k to y. Suppose from y basis to kx basis. This is the case. Okay, and also we assume that capital N equals to 2 to the power little n. Okay, and y has a representation in bit string as y1, y2 up to yn number of points, like bits. Basically, this is the binary representation for this binary representation. And if somebody sees the information in some books, they also write in this format. So it is equivalent to decimal representation as 2 to the power n minus 1 y1 plus 2 to the power n minus 2 y2, and so on up to 2 to the power 0 yn. So these are equivalent, right? This is like decimal representation. No, somebody is asking, Dr. Padmavati. Ma'am, Hadamard gate is the combination of 0 and 1 with different probabilities, right? Putting QFT only one state is shown here putting, but in QFT only one state is shown. Where it is, let me check. No, first of all, Hadamard gate gives you equal superpositions. Okay, so probability theoretically half. Okay, second is QFT. One state is shown. No, so one state means, so if you repeat the experiment multiple times, you will see the different states. Yeah, on Blosphere basically, yeah. So if you see on the Blosphere, if you apply Hadamard on the 0 basis, you'll be getting this state. If you apply Hadamard on the 1 basis, you'll be getting this state. So this is the answer. Like, so implication of the Hadamard gate on 0 state is plus state, and application of Hadamard gate on 1 state is minus state. So yeah, thanks. So now let's represent y as so this representation, decimal representation, we can combine them, and we can write them in this fashion, like y is basically summation of k equals to say 1 to 1 to some variable n, such that yk 2 to the power n minus k, right? And this is same as summation of k equals to n 1 to n yk 2 to the power n by 2 to the power k. Okay, so now let's try to write now let's try to write the ket x tilde, that is the Fourier basis representation, right? That is 1 upon square root n from definition, sum of y equals to this next 5 minutes is extremely important. Okay, y equals to 0 to n minus 1 e to the power 2 pi I x. I'm putting this summation here. Now this is k equals to 1 to n y power k by 2 power k. Okay, and here I am writing y1, y2, this entire bit string. So now entire equation I have converted to the binary bit string. Okay, Now, this is equals to 1 upon square root n summation of y equals to 0 to n minus 1. Okay. So we can also write this part as, this part is same. Now this part I'm writing as product of k equals to 1 to n, right? So e to the power of sum equals to product of individual e to the power, right? So if they commute basically, so we are taking independent components. So e to the power of sum equals to product of e to the power, right? So we are just converting this sum to product, e to the power 2 pi I x y k divided by 2 power k y1 y2 dot 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 yn. Okay. I'll take all the questions. So let me complete the derivation part. Then this part, let us break this part as y equals to 1, y equals to 0 to 1. The second component of this y is y2 equals to 0 to 1 and dot 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 up to yn 0 to 1. This summation we can break in this way. Okay. Then what is happening if you do these things? K x tilde will be 1 upon square root n. And this notation we already know from previous QT series. This is basically tensor product, right? Sum of product is tensor product. So, right. So this is, we already have seen like sum of product, right? So now the beauty like of this equation, right, comes up. Like we can now write it as k0 plus, now I'll take various values of k from 0, 1, 2, 3, 4 up to n minus 1. So what will happen? So each time I basically write in the tensor product form, it becomes e to the power 2 pi I x 2 to the power 1, 2 to the power k becomes 1, k to 1. First part, tensor product. Second part, so k0 plus e to the power 2 pi I x 2 square, k to 1, tensor product, dot dot dot. I can also write, okay, let's write the third part, tensor product. Now k0 plus e to the power 2 pi I x 2 to the power 3, k to 1, tensor product. I can continue, and the last term will be k0 plus e to the power 2 pi I x by 2 power n k 1. So this is just writing the same equation in the tensor product form. Okay, and this makes things much simplified. Why I have written this particular form? So swapping the order of the product and sum and bring in the terms of tensor product form, right? This is what I have done. So by breaking this way, what we have done, this is the Fourier transform part of the nth qubit. This is the Fourier transform part for n minus 1th qubit, and this is the Fourier transform part for the first qubit. So this is how the equation totally changed into the binary bit string pattern, right? And we'll see the complications, the recursive nature of the circuit, and basically now we can build. So those who basically haven't completed the equation to write in their note, you can continue. So now we can build a circuit for this, similar to what we did with Hadamard gate. Hadamard gets earlier. Okay. And the part is very simple, like applying Hadamard, but the only issue is are these phase terms. So Hadamard, it was like 0 plus K1 by square root 2, 0 minus K1 by square root 2, everything was fine. But now this extra terms is coming from the equations, e to the power 2 pi I by ix by 2 to the power 1, 2, 3, 4, 2 to the power 2, 2 to the power 3, 2 to the power 4. This extra phase term is coming. So the complexity that is arising with the, so 1 by 2 to the power n in the phase term, and that phase is not same everywhere, phase term, right? So now, no, only applying Hadamard won't help you, because only applying Hadamard is not giving you these equations. So you need certain phase gates as well, okay, in a controlled manner, such that this equation basically obeys. Okay. So now what is happening? Now Ktex, suppose the representation of Ktex is bit string x1, x2 to xn. This is a bit string representation of x. And from tensor product relation, we know this is x1 ket, tensor product x2 ket, tensor product dot 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 up to tensor product xn ket, right? This is the simple representations, right? And if we apply the QFT, quantum Fourier transform, and suppose we get the x tilde basis states, right, from the equations, right? And we came to know that this is 1 upon square root n. The first qubit becomes ket0 plus e to the power 2 pi I x by 2 to the power 1 ket1, so on, tensor product, so on. So now you can match, this becomes this, and this becomes like, say, this is tensor product ket0 plus e to the power 2 pi I x 2 to the power n ket1, right? So now let's take Ktex example. Suppose Ktex, say n equals to 3 qubit, right? And suppose you have the Ktex equals to 101 state. This is your initial state, and you are applying quantum Fourier transform on this. So Ktex tilde, that is the quantum Fourier transform of Ktex. Suppose you apply QFT, so it becomes this. So this is 1 upon square root 8 ket0 plus e to the power 2 pi I 5 by 2 ket1, tensor product, so on. The last term will be ket0 plus e to the power 2 pi I 5 by 8 is the phase factor here, ket1, right? So now there are more tricks how we can optimize, right, for n number of qubits. So we'll draw the circuit, but before that, let us try to understand what is happening. There is one more fact here. So if you travel right to left, travel right to left, then what is happening? So each qubit went from xk ket to ket0 plus e to the power 2 pi I x by 2 to the power k ket1, right? Now, so for example, this xk tilde, right? Sorry, x tilde. It contains, what are the terms it contains, right? So it contains. So the first case. So if all are zero qubit, so there is no phase, right? If the last qubit is only 1, so the phase factor is e to the power 2 pi I x by 2 to the power n. If the second last qubit is 1, but the last qubit is 0, right? Then the fetch factor is e to the power 2 pi I x by 2 to the power n minus 1, right? So this is one part. Second is, this is one thing we can see from right to left. Second thing that we can observe is uh, so e to the power terms, like all the fetch factor term, that if we take the sum, right, for the last qubit, right? So the last qubit is what? Last qubit is all one. Last quantum state basically is all one, right? So we can write the expression for this as e to the power 2 pi I, right? Uh, x by 2 plus x by 2 square plus dot 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 x by 2 to the power n. So this is a nice series, right? For the last, if you basically, if you multiply like all one, right? So here k1 k, if you come back to the original equation again, say this one. So tensor product of all one is the last qubit state, right? So that is the fetch factor is multiplied with this times all this fetch factor. So that will be x by 2 to the power 1, x by 2 to the power 2, dot 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 x by 2 to the power n sum, right? So this will be the fetch factor for the this particular qubit states, because ultimately your representation of the information will be in this basis states, right? All 0 to all 1, right? Although when you implement, you will be following to this breakup tensor product form, but ultimately mathematically the information is represented in terms of the n qubit representations. Okay, so this is the fetch part, right? And now this fetch part is qubit dependent, right? Fetch part is qubit dependent. So this is not so easy, right? So this is, every qubit has a different fetch factor now, and we need to add more circuit components with more ones in the bit string representation. So let me clarify these things. If you check left hand side to right hand side, see all this zero state has no phase, right? But all this one has all the phases, right? Which is basically is in some series equations, right? So why I am doing this and how I am doing this is basically your overall equation representation is basically the product of all this tensor product of all these equations, right? So this zero, all this zero will be multiplied, this zero, and all this zero will be multiplied with no phase factor. Then this zero will be multiplied with this, then all zero, right? So if you multiply all terms with everyone, right, then only you will be getting all the basis states, like all 0 to all 1, and more number of ones are there from right to left, more is the phase factor coming into picture. More 0 is there, less phase factor is there. So that is an observation from what is happening from the equation. Okay, so now many commented regarding this Hadamard gate, right? So what is happening? So how to design the circuit? I'll write the code as well. Okay, I'll show how the code is done, but let us understand it. So we started with the state xk, right? And we apply Hadamard gate, right? So till now we know that if we apply Hadamard gate on 0 state, we get plus state. If we apply on gate 1, we get minus state. This is what we know, right? But if you apply Hadamard on some arbitrary state x, what will happen? So the generic representation of any general state is gate 0 plus e to the power 2 pi I xk by 2 gate 1 by square root 2. Now you take xk equals to 0 and xk equals to 1. So if you will see that if you take xk equals to 0, you'll be getting plus state. If you take xk equals to 1, you will be getting minus state. So this is an arbitrary state representation with the Hadamard gate. Okay. So this is a form like applying Hadamard gate on some arbitrary state. This is the representation. And second is you have to apply something which is called U rotation gate. U rotation gate or the so U rotation gate, let me define certain thing. So U rotation K gate on the state xj is e to the power it does e to the power 2 pi I. It's a quantum gate. E to the power 2 pi I by 2 to the power k. This k is 2 to the power k. Okay. Xj gate xj. Okay. So if xj equals to, so this is the definition of U rotation gate. If xj equals to 0, then you put xj equals to 0 and it will become e to the power 2 pi I by 2 to the power k, and here it is 0, right? Ket 0. So it will be ket 0. So 0 times all these things will become 1 and it will be ket 0. And if ket j equals to 1, then it will be e to the power 2 pi I by 2 to the power k times 1 times ket 1, right? So it will be 2 to the power 2 pi I by 2 to the power k ket 1. So what is happening? If the qubit is 0, it does nothing to the qubit. It does nothing to the phase of the qubit. But if the qubit is 1, it just adds the phase to that particular qubit. So that is the purpose of U rotation gate. Sometimes we call it as controlled rotation gate. Controlled rotation gate. Okay, controlled rotation gate. So now you compare the equation. So this, if you apply phase gate, this ket 0 will be unchanged, but this ket 1 basically wherever there is ket 1, this phase you can add using this control phase gate. So mathematically, in form of the quantum gate representation, the definition of U rotation gate is U rotation k equals to the matrix 1 0. It does nothing to the quantum state 0 0 e to the power 2 pi I by 2 to the power k. This is the matrix definition. Now you apply to ket state 0, 0 will be 0. And if you apply 1, 1 will be e to the power 2 pi I by 2 to the power k, ket 1. So it applies phase e to the power 2 pi I by 2 to the power k to state ket 1. This is the purpose of this quantum gate. But if you apply this quantum gate to ket state 0, it will do nothing. So this is one important trick to design quantum circuit. And now we'll be seeing how to design the quantum circuit for this QFT. So the circuit part is pretty much easy, right? So this trick is important, how to design the thing. So suppose your all quantum state are like this, x1, x2, x3, all these qubits are placed like this, xn. So you apply the Hadamard gate first, right? So normally quantum circuit reads in a reverse way, and for which we need to apply swap gates in the output to make it in the proper way. So basically you need to apply all the U rotation gate, like U rotation, say with power k equals to 2. Okay, then again you need to apply U rotation gate with k equals to power 3 and so on up to say this n. U rotation gate up to k equals to n, say, and here are all other these branches. So first qubit you apply Hadamard, right? There is no phase factor. Second qubit, there is only one phase factor. So this control U rotation 1 gate. Third, you have action of 3, this, and this. Okay. So on. So this is the implication. So let me instead of drawing this thing, so let me share how it is implemented from the direct encoding part. Just allow me some time. So you can see this implementation here. So So this circuit, if you see, so x1 to xn, right, is the bit string representation. So first you apply the Hadamard and the one control gate, and you repeat up to nth quantum gate. So this is the first part of the circuit from first part of your equation, and you continue up to till the last part. So if you see the last quantum basically register, there is only one Hadamard gate, right? So that I was saying in the reverse order, right? So reverse order means there is no fetch factor, right? So no fetch factor means this represent all zero state, right? But actually it should be all one state, right? Opposite direction. So we applied the swap gate between this first and last chain, right? So this information will be swapped here and this information will be swapped here. So we continue this pattern basically. So, and if you come back to your second last, only one control rotation and one Hadamard. So that is giving you the second part of the equation, and so on, so forth and so on, right? So this is the way how QFT is implemented. And let me, I already shared the code, but let me again show you. You can basically, if you see in the equation of QFT, there is two variable X and Y, right? So that's why there are two for loop, one for X and one for Y. Okay. So one part you are applying the Hadamard, other part you are applying the controlled phase gate, right? So this is basically customed. Although there is direct function of QFT available, but still I wrote the custom QFT function so that you can understand. So number of QPT vary, you apply Hadamard gate and you apply control phase gate as per equation. That's the circuit done. Now, I have also shown an application of this for finding the periodicity of a function using classical FFT and using quantum Fourier transform, right? So this is the classical Fourier transform of an exponential function. And this is the quantum Fourier transform of an exponential function. Here you can see these discrete points are shown in the frequency bin. And here you can see those bins in the computational basis states after quantum measurement. So this is the basic difference. So this part I already have given you in the notes. You can look at, and if you have any doubt, I can take tomorrow. So with this, I'm closing this part of QFT today, but I'll continue quantum phase estimation and other things, and I'll continue the source factoring algorithm tomorrow. So let me know if you have any question. Any doubt, or it was very difficult session, or it was very easy session, or anything?
Sir, there is one question. Does a quantum fast Fourier transform also exist?
Okay, so quantum Fourier transform exists. Quantum fast Fourier transform, there is no terms as such. You can give a try. So yeah, thank you so much. I think there is no question answers. How to break quantum computing? Okay, RSA algorithm. I think QT-06. Many people will talk on quantum communication next course, so I won't talk much. But source factoring tomorrow again, I'll continue. Yeah. Normally, I keep the topics keep if there is more sessions on other courses. So right. Yeah. Thanks.
Sir, can we apply fast Fourier transform to quantum image processing? Dr. A.C. Nagesh is asking.
Okay, can you apply fast Fourier transform to quantum image processing? Okay, first of all, the classical FFT you cannot apply on quantum image encoding. So it will be QFT applications on the image processing, definitely. So the way I defined is a one-dimensional representation for the QFT, right? So classical image processing, people apply normally 2D FFT, okay, two-dimensional. So in images, normally you have X coordinate and Y coordinate, each pixels how you define, right? So similarly, you can design or try to design QFT for two-dimensional positions. Here I represented X to KTX. You can try to design a circuit for X, Y to KTX, so tilde X, tilde Y, that kind of circuit. that can be innovation or research problem for you. And definitely for various image processing problem, for example, noise elimination, various frequency component find in images, like particular feature detections, right? Image classification. There are many applications you can work for. Yeah. So 1D QFT to 2D QFT, two-dimensional QFT can be a good research problem you can think of if somebody has not done yet. Yeah. Thank you so much.
So that seems to be all the questions.
Yeah, I have seen the question. So most of the things are already covered. Some of the question I will bring forward tomorrow. Yeah. Yeah.
Okay.
Thanks. Thanks a lot.
Okay. Thank you, Dr. Mustafizur Rahman, for this very informative session. I hope whatever questions you have, you can email, right?
Yeah, sure.
Uh,
Email or send it me through LinkedIn or anything like
yeah.
that.
So he can cover in the next session by itself, right?
Sure.
Please be on time, and thank you, sir, for this very informative session. So with this, we are going to close today's FDP session. Thank you, sir.